Thank you all for joining us for the second colloquium of the term. We are very pleased to be hosting Professor Zoltán Haiman from the Institute of Science and Technology, Austria. So Zoltán did his PhD at Harvard and actually spent a year here during that, after which he spent a year at Fermilab and then took a Hubble Fellowship to Princeton. And after that, he was at Columbia University for more than 20 years, impressive tenure there, and then moved to ISTA last year. And earlier today, I learned that he has done a great deal in a very, very impressive swath of fields, ranging from weak lensing cosmology to the high redshift universe, as well as what we will hear about today, which is binary black holes. So without further ado, I'm very pleased to welcome you and take it away.
Yeah, thank you very much for the invitation. It's really a pleasure to be here. I get nostalgic every time. Yes, I spent a year here. My PhD was on the high redshift universe. So this is a different topic, but still I feel a strong connection, and I'm actually closer now. So it's great to be here. And I also had really, really nice conversations throughout the day on many topics. So it was really stimulating. The talk will be on binary black hole mergers, and these pictures are to make the point that they emit gravitational waves, so they're already very exciting these days since the discovery from LIGO 10 years ago. But if they're surrounded by this merging binary surrounded by some plasma, it's even a more rich phenomena, and you can do even more list of great scientific things. So, and these are just to list my collaborators who are students and postdocs and faculty. And then I just want to start by one slide, which is not scientific, but I polled people, and I think about half of you have not heard of this institute. So I just wanted to point out that I moved a year ago from Columbia University to this place, Institute of Science and Technology, ISTA. This is the campus. All the buildings are pretty much built in the last 10, 15 years. And this campus is located here. Oops. This is Vienna. This is about half an hour from Vienna in the hills. And it's an interdisciplinary institute. I am the 5th astronomer. These are the first 4. And hopefully the institute will be hiring more astronomy faculty in the next 5 to 10 years. The outline of my talk is I hope to cover is first I want to give you an introduction of what's nowadays called multi-messenger astrophysics, which essentially belaboring the advantages of discovering a binary, both gravitational waves and electromagnetic spectrum. And then these two parts will be theoretical, based on simulations of binaries with circumbinary disks to address the orbital evolution, how a coupled system of binary and a circumbinary disk might evolve over time, and then how it might accrete and produce electromagnetic signatures which distinguish them from single black hole of the same mass, accreting at the same rate. And then I hope to get some time to discuss the observation situation of black hole binaries. And if by magic I finish early enough, I want to comment on stellar mass black hole binaries. Most of this talk will be on massive black hole binaries in galactic nuclei, but a lot of the theoretical results also apply to stellar mass black holes, should they have circumbinary gas disks. Okay, so the first, I want to start with the introduction very briefly. I'm sure all realize there's a spectrum of gravitational waves that can be produced by coalescing black holes, which are covered by 3 different instruments, very different types of detectors. LIGO on the ground is sensitive to kilohertz gravitational waves and the stellar mass black holes. Pulsar timing arrays are sensitive to nanohertz gravitational waves, probing billion solar mass black hole binaries. And in between, in the millihertz frequency, are the 10 to the 5-6 solar mass black holes, which are detectable by the space-based interferometer LISA. And one reason I show this diagram is that these massive black holes, we think, are produced in mergers of galaxies, and those mergers drive not just the black holes to the nucleus to cause a binary to be present, but also drive gas to the nucleus. So maybe your naive first assumption is that these mergers take place in a gaseous setting, whereas the leading models for how the LIGO mergers are produced generally don't involve any gas. The merger in both most popular channels happens in vacuum, but I put question marks here. It's quite possible that massive black hole binaries merge without gas, in which case you can forget my talk because it won't be relevant. In the case of stellar mass black holes, on the other hand, there is a chance, I think, that the LIGO event happens in a GANS disk, which is very dense and can produce even electromagnetic flares. So that's the gravitational wave side. Now, the massive black hole, and also the reason I'm mostly focusing on massive black hole binaries. These binaries are produced in mergers of galaxies, which we know galaxies are built up by mergers, and we know they have massive black holes in their nuclei, and we know that black holes are very heavy compared to the stars and dark matter particles, so they shrink to the new nucleus of the merger remnant. And then if they manage to get very close, they will be gravitational wave sources, detectable by these detectors. But much earlier in their evolution could already be producing electromagnetic signals, which can allow us to pinpoint that they're binaries. And I have one slide here just for motivation of what you can do if you detect gravitational waves and photons from these objects. And this, of course, is now a growing list. I just have it broad categories, but for astronomy and astrophysics, this would be quite revolutionary. We could, for the first time, study directly how quasars and galaxies co-evolve over time, because we would see which merger takes place in which galaxy and which black holes over cosmic history lived in which galaxy. We could study accretion physics, where, because we'll know the parameters of the gravitational wave source, masses and spins, and even the orbits, and then we can study light curves and spectra as a function of these, which will be a unique setup. And then we can study the environments of merging black holes if we know which galaxy comes from and what is the nucleus of the galaxy look like. And also, if we see distortions in the gravitational waveforms in a particular galaxy, then we'll learn about the environment through the gravitational waves deviating from vacuum. There's also fundamental in physics and cosmology applications of this so-called multi-messenger astronomy. One is that you have standard sirens. I'm sure I don't have to explain this. The Hubble diagrams, which resulted from supernovae in the discovery that the universe accelerates its expansion, can be done with chirping gravitational wave sources, where you have the distance from the gravitational wave signal to a binary black hole in a distant universe. And if you have a spectrum of the source galaxy or the binary itself, then you can determine its redshift. And then you have this Hubble diagram, which I think the most exciting part, well, which extends the supernova cosmology to higher redshift with different systematics, but also the distance measurements come from gravitons, not from photons. So you can study how the supernova and the standard siren Hubble diagrams look like. They should agree. If they don't agree, that can probe deviations from general relativity. Also, if the gravitational waves travel at speeds lower than the speed of light, you can find different time of arrivals, which would probe the mass of a graviton if it's not zero. And even extra dimensions, gravity gets weaker in theories with extra dimensions, which would modify the Hubble diagram for standard sirens compared to supernovae. So on the other side, is there some practical benefits? For example, if you have a marginal gravitational wave detection, but you have a source in the sky, you can solidify your detection. And also, if you know where the source is located in the sky and in distance, you can break parameter degeneracies in the gravitational wave analysis, which helps determine the other parameters. So all of this is a lot of motivation to find either an electromagnetic counterpart to a gravitational source, or at least the precursors. Some of these can be done with just populations, precursors of gravitational wave sources in electromagnetic observations. So the questions to answer for this is, well, I have this merger of galaxies, I have a pair of black holes in the new nucleus, but how do these pairs of black holes evolve, and how do we actually find them before gravitational wave, other than in electromagnetic observations? So the approach to take, so now I'm turning towards what we've been doing about all this. The simplistic way I think of this is that we have a cartoon picture how a single black hole quasar operates if it's sufficiently fueled. It's accreting through a geometrically thin, optically thick disk, the outer parts of which are gravitationally unstable, and they fragment and probably form stars, and gets complicated. They connect to the rest of the galaxy. The inner part of this disk is gravitationally stable and in roughly Keplerian laminar motion. So you can then ask the question, if this is the case, well, first throughout this talk, I'm going to just focus on what happens here in this inner region, which is roughly below a parsec. So I'm going to just assume that the pairs of black holes have somehow navigated down to a separation where their separation fits into this stable part, which looks reasonable based on hydrodynamical simulations in the galaxy size context. Then you can just think of what happens if you put a second black hole here. How does a disk look like? So this is actually very nice because it's a very well-posed problem. I have 2 point masses and near Keplerian accretion disk, and you can ask the presence of the disk, how does that impact the orbit of the binary? Does it help, or does it hinder the merger of the black holes? And also, can the black hole actually binary merge in the Hubble time? This is also important for observations because the faster the binary decays its orbit due to the gas disk, if it decays, the fewer there will be on the sky at any given time. Then for electromagnetic signatures, you want to know how the black holes accrete in the binary setting. Does the gas get near the black holes, let's say 10 to hundreds of Schwarzschild radii, to power bright emission, similar to quasars? And how does this accretion happen? This obviously is important for EM observations because we want to determine what we expect for total luminosity, spectrum, and variability. Finally, for gravitation waves, there's a question of can we actually see this electromagnetic emission even at the very last stages of the merger, when the in-spiral is driven by gravitation waves and is very fast. And also, another question is if the orbit is actually modified by the presence of the gas disk, should gravitation wave observations worry about this, that the waveforms will be different from vacuum? The other motivation I kind of already alluded to is that it's just a very well-posed problem. 2 point masses with an initially Keplerian disk. And you can ask all these questions. So it's kind of fun to study. So let me first focus on the orbital evolution. And just more context, I should say that this field has a formidable literature by now. And and it's very hard to do analytic work because the system, as you will see in a moment, is quite complex, even in the simplified hydrodynamics setting. So you can do some kind of assumptions that there's some steady state behavior of a binary with a disk and try to do theoretical calculations. I will not talk about those. You can also try to do axisymmetric one-dimensional calculations where you're just interested in the shrinking or expanding of the binary orbit and some disk, but you'd have to assume some axisymmetry. So really, to make any reasonable statements, you should do at least 2D and ideally 3D simulations. So I'm going to exclusively talk about 2D simulations here, which is justified in some sense because the disk can be quite thin. We think accretion disks around quasars are quite geometrically thin. And also these simulations are much less expensive than 3D simulations. So just for reference, for 3D, there's also many papers that are now looking at binary accretion in 3 dimensions, but the number of orbits is very limited. And as you'll see, it's actually important to determine the behavior of such a system to do thousands or even tens of thousands of binary orbits before you settle into some kind of equilibrium behavior. So I'm not going to discuss we've been doing this for the last 10 years or so. Most recently, we've been using last 4 or 5 years this code called Sailfish. This is a great code. It was not, I have nothing much to do with it. It was written mostly by Jonathan Drake, who's a former postdoc at Columbia, now Clemson faculty. This code is great because it runs on GPUs, so it's more than 20 times faster than the code we previously used to do comparable simulations. Basically solves the Navier-Stokes equations, vertically integrated, and it's just pure hydrodynamics. The black hole's potential can be deviating from 1 over r to mimic relativity in a post-Newtonian potential. The most important physical ingredients that we've introduced to compare to most previous work is that we solve the energy equation. So the gas is heated by viscous dissipation, and also by shocks, which you will see in a second occur due to the binaries' severe disturbance on the disk. There are lots of shocks which heat the gas. And then there's cooling, which here we just assume the simplest thing you can assume, which is that it's an optically thick disk. It's emitting blackbody radiation from both the top and the bottom, with the temperature that's followed by the simulation. The black holes are actually on the simulation grid. They accrete with the sync prescription. And then, most importantly, these are 2D simulations, relatively cheap, so we can extend the disk very far out. So we're not sensitive to numerical issues at the boundary. And also we can run 10,000 orbits or even more to settle the system to a steady state. And then in this setup, there's really only a few parameters that you should understand how they're important. The binary has a total mass and the mass ratio, m2 over m1, and eccentricity. And the disk has an initial temperature, which equivalently can be the Mach number, orbital velocity divided by the sound speed of the gas. And then the viscosity is parameterized through this famous alpha parameter, which is mimicking what we think is an effective viscosity of a disk of a near Eddington bright quasar. Then when we do this, we can measure the gas morphology and the torques on the binary and everything I said before. I should say there are others who are doing this, and there are very similar results with different codes, Arepo, Athena, Gizmo. So I think there's reasonable reassurance that numerically we understand things to some level, accuracy. Okay, so without further ado, you can see here the result of, let's say, the most basic of such simulations, which in this case was done by a postdoc, Ryan, and the black holes here are equal masses. They're on circular orbit. The total mass is actually important because we solve the energy equation. So there's actually a scale in this problem. So this is a 10 to the 6, 8 times 10 to the 6 solar mass binary, two Milky Way black holes colliding. The Mach number is 10. The viscosity is 0.1. And what you see here is the top view of the surface density of this disk. And you can see it's quite distorted. And there's some very, very conspicuous features. There's a large cavity here. There are two black holes which however are not naked. They endow. And this you can also see by eye happens periodically. You can also see this cavity is quite lopsided. And all of this is quite important for everything else I promised to say. Oops. So this movie is actually on YouTube. So again, just to summarize, so these features are ubiquitous. All the people who do simulations would agree with all of these. So there's this central cavity. It's roughly few times the separation of the binary. The density is very highly suppressed. And this can actually be explained by the lack of stable. So this can have a theoretical explanation, because if you put test particles in this region, there are no stable orbits for particles to follow. So they'll naturally be ejected. The cavity is lopsided, and there's a lump here, and that's not explained by any theory as far as I know, why it's not circular, but it clearly has to do with the fact that the streams that you saw in the movie, they are regurgitated and they strike the wall of this cavity, and this process runs away and causes this cavity, the inner edge of this disk, to be very lopsided. That's also seen by everybody, and the important thing for us is the streams penetrate the cavity and feed the black holes. I like to point out that the reason that the gas can navigate from here, so the gas is coming from large radii, and that's through viscosity, so that's a standard. If this was an MHD simulation, this would be done by the MRI and the so-called magnetorotational instability, and the gas is viscously transferring angular momentum and arriving here. But then from the edge of this cavity down to the black hole, I don't think has anything much to do with viscosity. It's simply shocks and hydrodynamics. There's a propeller motion of this binary, creating shocks and pressure gradients to build up, which change the angular momentum of the streams of gas, and they navigated in directions that arrive within the tidal capture radii of the black holes and join these mini disks. So this accretion technically is not viscous accretion. This is hydrodynamical accretion through shocks. And then these mini disks, which you saw, are periodically fueled, and the net accretion rate of these disks, these mini disks, is actually not really suppressed compared to a single black hole. I'll show that in a second. So first question I promised to discuss is, how does the binary evolve? And we're most interested in, this is again such a simple setup. We're interested in whether the semi-major axis shrinks or expands, whether the eccentricity grows or decays, and then the total mass growth rate is interesting in terms of basic how luminous this system can be, but also whether the mass ratio is changed by the long-term accretion. So this is actually very interesting. For gravitational wave sources, of course, you could say the number one most interesting question is does the binary shrink or expand? Actually, I like to poll the audience sometimes. You could raise your hand if you think the binary will shrink because of the gas. Okay, now raise your hand if you think the binary will expand its orbit. Okay, so most people didn't raise their hands. And I think they are correct, actually, the people who didn't raise their hands, because this is very, very unclear. I can give you now an answer in the simplified setting of this simulation, but the answer seems to depend on even these simple parameters. So basically, here is a picture from a same kind of simulation I just showed. On the top left is the surface density, but now it's orbit averaged. So we're not interested at the moment in the fluctuations, just over long time scales, what happens to the binary. So this is at average surface density over 100 orbits. On this side is the same simulation. This is the torque surface density. This is the color bar. So what this shows is the torque exerted by the gas on the black holes per unit surface area. And green is positive, purple is negative, so obviously, and this gas, the black hole is moving counterclockwise, so this gas, the green, is in front of the moving black hole, so it's exerting a force pulling it forward, so it's increasing the angular momentum of the binary. The purple is behind the black hole, it's pulling it back, it's trying to reduce the angular momentum and shrink the orbit. So what the net torque is the two-dimensional integral of this plot. And you can see by eye that you can't really tell whether the sign is negative or positive because it looks kind of symmetric, back and front, but when you look more carefully, it's actually not symmetric, right? There's some small differences, but mostly here. And so when you do this two-dimensional integral, this disk has a Mach number of 10, the gas disk. And when you do this integration, this binary actually expands its orbit. And that's caused by the fact that this green is slightly more dense than the purple behind, and there's this extra little thing near the black hole. And so there's a little more tugging by the gas in front of the black hole than behind it. So you should think of this as a cancellation, as a residual between two large numbers. There's a large negative torque, there's a large positive torque, and the net is actually positive. So that actually, this result was discovered 5 years ago and as I said, several groups. This was quite potentially disturbing because if you want to create a gravitational wave source, we don't want gas to not allow the merger. We want the gas to help the merger. So if you have this ulterior motive of trying to create a gravitational wave source, this was disturbing. Now, there's no, again, this is a case where I am not aware of any approach theoretically to try to derive the shape of the gas distribution here. There's analogous work on how planets move in protoplanetary disk, where you can do linear perturbation theory. There's just, I'm not aware of a productive theoretical approach. So the only way you can convince yourself this is okay, this result is correct, is do compare numerical simulations from multiple groups. So this was done the last couple of years. 6 or 7 different codes give the same result. SPH codes, grid codes. If you give the same initial conditions, they give the same result. So now, however, this is very sensitive to the gas distribution here. So here's another simulation, which is the same as above, but we made the temperature of the disk 3 times, the Mach number 3 times higher, or the aspect ratio 3 times lower. So it's a 3 times thinner disk. You do exactly the same calculation, and you can see what happens when the disk is colder. You can see here in the color bar that there's more gas density that piles up here compared to here. And you can see the purple behind is stronger than here. So what happens is this binary is now inspiraling. The gas is actually causing in spiral. And the claim is that this actually is a much more realistic, well, it's more realistic because we think disks of quasars are actually quite thin, even thinner than this, maybe more like 0.01. They're just harder to simulate, which is why everybody tended to simulate this Mach number 10. So the bottom line from this is that the circumbinary disk, if it's cold, it's actually is indeed promoting the coalescence of a binary, a circular binary at least. And moreover, the time scale A over A dot on which the binary shrinks is essentially tied to M over M dot, factor of few difference. It can be negative or positive depending on this Mach number, but it's this order, which means, and this m dot is the accretion rate on the binary from far away, out here, far from the binary. So if this is a near Eddington quasar, but have two black holes in the middle in a thin disk, it will actually merge in relatively short time scale of few times 10 million years. So that's good. Now just to quickly comment on the other two aspects, eccentricity and mass ratio. The eccentricity is also interesting. These binaries, it turns out they don't stay circular. So what you see here is a result of a suite of simulations. They're exactly what I just showed. The only difference is the initial binary orbit is not circular, it's eccentric. The binary orbit in these simulations is held fixed. So we just do, let's say, thousands of orbits at a fixed binary orbit, and we measure not just A dot, but we measure E dot, what happens to the eccentricity, and as a function of eccentricity of the binary. And this is d log m, so this is the change in eccentricity per accreted mass. And you see here the following. For high eccentricity, it's negative. So this part here makes eccentric binaries less eccentric until you get to this position of about 0.45. These binaries which are below that, the E dot is positive, so they're driven up in eccentricity. And this point here is an attractor, 0.45. So gas disks actually tend to create eccentric binaries, unless you're down here, where you start from already almost circular, then it just remains circular. So that's also interesting. Finally, the mass ratio. This one is actually very old result and easier to understand. This is another suite of simulations, circular binaries. As a function of mass ratio, this is m.2 fractional m.2 over fractional m.1. So this just shows that if you make the binary very unequal mass, 0.1 let's say, then the lower mass object accretes much more. And I don't have a movie here, but this is actually easy to understand. If you have an unequal mass binary, the lower mass one makes, the heavier one is near the center of mass. The lower mass one is farther displaced from the center of mass, and it kind of gets first pass near this cavity and is capturing more of the gas. So the accretion tends to equalize the masses. This is actually very nicely illustrated afterwards in a work where there's now a suite of simulations which are as a function of eccentricity and mass ratio. So far I told you that a cold disk causes in spiral, a warm disk causes out spiral on this time scale. Circular binaries equalize their masses, and equal mass binaries become eccentric. This is a suite where each point is a initial eccentricity and mass ratio, and each star is a binary, which is then can be followed in this 2D space. And the color is whether it's in spiraling, which is blue, or out spiraling, which is red. So you can, this is also a movie. So you should be able to see. What happens is the binaries are moving on this plane. First, they move to a non-zero eccentricity along this line. And then if you wait even longer, they're moving towards equal mass, so this point that I was just talking about. Okay, so this is what you expect, and I just want to show one. If this was actually the correct story, and you look at binaries with circumbinary disks, which are coplanar with the binary, so kind of 2D systems, you would expect them to be around this line. And just to show a teaser, I was amazed that there's this comparison with stellar binaries. So you can actually look at stars in our galaxy, which are in binary systems, and there's a very small number shown here on the same plane. I think I ran out of pointer, but this is a binary eccentricity of stars in our galaxy, and this is their mass ratio. And there are some, in particular, these 1, 2, 3, 4, 5, 6, 7, 8. These 8 crosses, there are 8 stars in binaries for which we can measure very accurately the orbital parameters, the eccentricity and the mass ratio. And we also see that the disk, the circumbinary disk, is coplanar with the stars. There's also a bunch of other binary stars which have polar disks perpendicular to the orbital plane of the star, so we exclude that from here. And then you can see that the red, sorry, this is run out of. This red curve here, that's the copied over from the simulations. And you can do Bayesian analysis by eye to ask whether these 8 points are randomly distributed or hypothesis 1 or hypothesis 2. They're scattered around this line. And I did by eye, and I concluded that the Bayesian factor favors the tracing the line. Of course, it would be nice to do this with many more stars. And I would even be shocked if this turned out to be a correct match, given that the simulations are quite oversimplified, but perhaps some indication that it's along the right track. Okay, so summary of this part is that binaries tend to in-spiral to this state where they're eccentric and equal mass. They forget their initial conditions after they accrete a non-negligible fraction, maybe 10, 20% of their original mass. They reach this state. Now, once the orbit shrinks to a separation of about 100 Schwarzschild radius, or a few hundred Schwarzschild radius, gravitation waves take over and causing very rapid in-spiral and very rapid circularization. And I'll return to this because then you have to ask, is the gas disk still look the same way as I was describing when this runaway happens? I should just make the point that the gravitation wave in spiral timescale is very, very steep function of separation. It's the 4th power. The gravitation wave power goes like a to the minus 4. So there will come a separation where inevitably the system runs away due to gravitation waves. Maybe I should skip this for now and make sure I have some time for the EM signatures. So the second part, third part of the talk is to discuss what kind of EM signatures we might expect from coalescing binaries. So again, just to start with a broader picture, this is the merger. We're talking about before merger, after merger, and before the merger we have this binary that I just discussed. And these times listed here are related to a Lisa source. So let's say 10 to the 6 solar mass binary. So you have this circumbinary disk and periodic accretion and variability for maybe hundreds of thousands of years. Then you shrink, then you start shrinking due to gravitational wave emission. And then a few years before merger, you might be detectable by LISA, the gravitational wave detector in space. And now it's a gravitational wave source. And then at the very end, things can get very violent because the in-spiral is so fast. I will comment on that. Maybe there were suggestions that there might be a strong flare at that point. And I'm going to claim that that's the opposite. We might have actually a rapid disappearance of a quasar at this time. Now, after the merger, the gravitational waves are emitted. They're very bright in gravitational waves. And then I think you probably all know that during the merger, you lose energy and into the gravitational waves, and you also lose momentum in the gravitational waves. So the remnant black hole will have a loss, a mass that's smaller than m1 plus m2. And also it will recoil at velocities of order, typically, depending on spin and orbital parameters, could be hundreds of kilometers per second. And this mass loss and recoil of the remnant can cause shocks in the surrounding gas disk on timescales of weeks to months to years. And then once you have a single black hole instead of the binary, this cavity will be filled in presumably then on the viscous time scale, which can be years or decades. So let me start with the, I think I have mostly things to say since I focused on the binary simulations on this part. And if you take home anything from the talk, you should just take home the message that binaries, if they really have a gas disk around, they'll be periodic sources on the sky, periodically fluctuating. And so there are actually, I'm going to tell you 3 reasons for this. One is the simulations I just showed. These are binaries with different inclinations. So I'm trying to illustrate with this plot here that hydrodynamical modulations, which you just saw in the movies I showed, cause fluctuations periodically, irrespective of inclination of the binary with respect to the line of sight. Now, if the binary is not face-on, but has some edge-on component, then you will see Doppler modulations. And then if the binary is quite edge-on, then you can actually, so this is then you can see gravitational lensing if you're sufficiently edge-on, and you see periodic flares from lensing. So let me discuss all of these quickly. So, well, this is maybe just to make one point. So these are accretion rates measured in binary simulations, and these are nearly equal mass. These are on the right. So mass ratio is 0.7. On the right, the mass ratio is 0.1, so 1 to 9. And the top shows accretion rates, and the bottom shows Fourier transforms. Green and blue are first black hole and second black hole. So this is just some obvious things. And m.0 is a reference simulation of a single black hole with the same mass, m1 plus m2. So the first thing to notice is that this is order unity on the y-axis. So the total accretion rate on the binary is basically the same as a single black hole. So even though you have this cavity, the binary is accreting just at the same rate as if it was a single. So that's good. It can be bright. You can see that the accretion is periodic. You can see by eye, this is here 25 orbits during the simulation. You can see orbital modulation on the orbital time scale, and also you see a modulation on the longer time scale, which has to do with the lump that I introduced. This cavity is not circular. So there's also modulation of the accretion rate on this few times the orbital time scale of the binary. The unequal mass case is actually quite interesting. As I mentioned before, the green is the lower mass object, which out-accretes the primary black hole by a lot, and is even cleaner periodic fluctuations. The primary is accreting much less and is actually quite steady. These are Fourier transforms. Well, since I said the binaries become eccentric, it's also just nice to show you what happens in the simulation where you make the binary eccentric. And you basically, the main difference from a circular binary is that this cavity is now very lopsided and very large. It doesn't really affect the accretion, what happens out here. And so basically every time one of the binaries goes to the epicenter of the orbit and goes close to the cavity wall, it spills off a stream. So you get a much more bursty or less sinusoid-like variability. So again, I don't want to go too much into detail because the main message is periodicity, but these are circular, these are eccentric, these are colder, these are warmer. And you see they're all, and these are actual predictions, optical and infrared. They're always periodic. You see the 2 time scales. If it's eccentric, it's more sawtooth-like, kind of more spiky. And of course, what I'm going to try to say in 15 minutes is that you can look for these periodic modulations in quasar light curves. But before I do that, I just want to return to the 2 other effects. So suppose you don't believe anything I said about the simulations. There's still 2 reasons that the binaries will be periodic. So one is Doppler effect. This is special relativistic Doppler effect. And this is the picture of one of the simulations. let's say the observers are down here, you're looking at the binary, clearly this black hole is coming towards us, this is going away from us, and if this gas here is bound to the black hole, which is inside its tidal truncation radius, then there will be V over C modulations in the brightness following the radial velocity or the component of the velocity along our line of sight of that order. So the light curve should vary periodically. Now the V over C is of the order of this variability, but interestingly, this V over C is actually not very small. So for example, if you think of quasars, which are powered by 10 to the 9 solar mass black holes, and let's say they have orbital periods which are humanly searchable in a human lifetime of order a year, a 10 to the 9 solar mass binary with a period of 1 year has a V over C of order 10%. If you think of a LISA source that's entered the LISA band, this I haven't explained, but LISA is sensitive to millihertz, so orbital periods are of order half an hour, let's say, when you enter the LISA band, and the masses are lower, 10 to the 5, 6 solar mass black holes. V over C is also about 10%. So both for quasars, bright quasars, or for LISA sources, this should not be negligible in principle. And I don't know if I have time to comment on this, but this is actually particularly useful because A, we know the shape of this variability, and B, this should be chromatic because the modulation depends on the spectral curvature. So if you're doing a photometric light curve and you're looking for this Doppler effect, if the spectrum is steeper and it moves up red, blue, you'll have larger modulations on the y-axis. If you have flatter spectrum, it will be less amplitude will be less. So you can check this theory if you see a source like this, which I hope to find 2 minutes for a candidate to show you. You can, in principle, test this by looking at chromaticity of the periodic variation. Okay, now the most fun part for me is gravitational lensing. I actually used to show this plot, the movie. You've all seen the movie Interstellar, so you know what the black hole looks like when if it was imaged. So this image here from the movie shows actually an accretion disk that's almost edge-on, but you see that you still see an extended ring on our sky and a large black shadow. I no longer show this, have to show this because this image actually is well known, I think, to everybody. Such images were made in the radio with the Event Horizon Telescope of two galaxies, M87 and Sagittarius star. And they don't look like that, but they do show the shadow and the bright ring. Actually, one fun aside is I like to show, I didn't bring that plot, but the Earth and the Moon have the same angular size on the sky because the size ratio intrinsically is the same as the distance ratio. That's practically the same with these black holes. M87 is 2,000 times larger than our own black hole in the Milky Way, but it's 2,000 times farther. So these are actually pretty much the same angular size by coincidence, same as the Sun and the Moon. And therefore we have these two images. The reason this is interesting is that now I'm talking about binaries. So you can ask yourself, if I have a binary, so this is a work that we did with a postdoc, Jordi Davelar. Suppose you have a binary that looks like that, but then there's each black hole looks like that, but the foreground black hole looking from the Earth, if they're in conjunction, then you have to do this processing of the lensing twice. So this should be interstellar squared or something like that, because you do that processing of the image twice. So Jordi, who was actually involved in EHT, had written a ray tracing code which solves the geodesic equation, so we can actually create images. So for this, to make things simpler, we just painted a smooth circular mini disk on each component of a binary. And then, but then we did the processing of the image due to relativity GR accurately. And this is the movie. So you see the shadows, and then you see that when the black hole goes, the background black hole goes behind the foreground one, it kind of wraps around, and you get this complicated image. Now, why is that interesting? Because this is another binary signature. So these are snapshots from this kind of simplified movie. Blue is the black hole in the front, going towards us. Red is the one in the behind, going away from us. And so it has it's lensed into two images. And these are near conjunction, and then just right at conjunction. Of course, we don't really have a hope of resolving this unless we happen to have a very massive binary very close by, which doesn't seem to be the case. But you can integrate this light and plot the total flux or luminosity you would observe. That's shown in the bottom. And you can see that there's a characteristic recurring flare that happens, in this case twice per orbit, because we assume both black holes are bright. And so that's another binary signature. It's periodic. It should be quite accurately periodic because it's just due to the geometric lensing. There's two more things I want to say about this. One is that this might sound like very exotic, like you have to be very fine-tuned and very close to edge-on to see this. So it turns out that's not really the case, because if you're lensing, if you work on lensing, you know what the question is, what is the projected separation of the binary in units of the Einstein radius? So if you plug that in, then you get this result, that the angular size of the binary in units of the Einstein radius is the binary separation in units of Schwarzschild radius to the -1/2. That means if you have a binary that's separated by 100 or a few hundred Schwarzschild radii, then square root of that, inverse square root of that is 0.1 or 0.1 or a few percent. That means few percent or even 10% of binaries will be such that the orbit of the binary is smaller than the Einstein radius. So it's not a tiny fraction for compact enough binaries, which are both LISA sources and current quasars. So this should be visible. And then I should just point out that the shape of this is quite interesting, because the size of this shadow is, as you know, it's about 5 times the Schwarzschild radius. Can cause a dip on top of this flare, because when you're really aligned and you're trying to lens this shadow, then there's no emission there. So right on top of the flare, you get a dip. So therefore, we conclude that this is another binary signature, recurring flares with potentially with dips. Of course, this is a toy model. In reality, the quasars flicker and there are fluctuations on the light curve, but the hope is that you can average over enough cycles and stack such periodic recurring flares. This kind of feature might emerge. Okay, I'm going to skip this. So I only have a few minutes. Actually, how many minutes? 5 minutes. So let me address one issue which is important, particularly for LISA. So the question is, are these signatures still present for a LISA source? Because the LISA source has kind of run away. And so the picture you might have in mind is that there's a binary with a disk, but then at some point the in-spiral due to gravitational waves is much faster than the fiducial viscous time in the disk. And then the binary runs away and merge, and maybe the gas was completely left behind. And therefore you just have a completely dark event in photons. And so to address this, Luke, a student at Columbia, ran the same kind of simulations I showed before, except the binary orbit is now circular, but not fixed. It's in-spiraling due to prescribed by gravitational-wave emission. And these are the light curves you get from such a simulation. This is again two Milky Way black holes merging. This is 15 to 10 days before the merger. This is the last 5 days of the merger. And these are X-ray and UV luminosities. And what you see here is basically, you still see the periodic variability, you see the longer time variability, you see some diminishing of the luminosity, but not a lot. So that's basically, I want to show you why that is. So this is that simulation where the binary is in spiraling. The left is the density, surface density. The right panel is the temperature distribution on the disk. And this bottom shows you the light curves, optical, UV, X-ray, and the total bolometric by integrating the emission from this surface at this temperature. This is 5 days. This is the last 5 days of the merger. And you can watch the movie. And you can see it looks a bit different from what I showed before with the fixed orbit, because the binary is running away, so it's generating a lot of these streams which are filling up this cavity. There's still 2 mini disks there which are still fed by these streams. And now we're 3 days before merger. Nothing really noticeable has happened other than this morphology. But something dramatic will happen in the last day of the merger. If you watch these mini disks, what happens is, okay, we have to wait. And the movie is, the frames are not correct, but you saw that the mini disks suddenly disappear. So what we found here is, in retrospect, something quite easy to understand. When the separation of the binary shrinks such that this tidal radius inside which you could have stable particle orbits becomes smaller than the innermost stable circular orbit, the ISCO. At that moment, you can no longer have a mini disk feeding the black hole, and they just destroy it completely. You could see from the temperature plot that it's hotter near those mini disks, so the X-ray emission is entirely coming from these mini disks. And so basically in the last day, the green here is the X-ray luminosity. It drops by 4 orders of magnitude within the last day, just because you disperse the mini disks. So that's quite interesting. That means if you're seeing a LISA source on the sky, it's merging. You could look in the error box of LISA, and hopefully there won't be too many quasars, but there'll probably be at least a handful. And if you can monitor that area, one of them will just completely disappear in X-ray. There will be a smoking gun that you saw there, the binary. So I think I need to actually stop, unfortunately, for the rest. So maybe I'm just gonna go back to my summary and say I won't show slides because we're out of time, but I should just summarize and say that based on what I've just said, we and others have looked for periodically fluctuating quasars. And this is another several slides which I don't have time to show, but the bottom line is that there are candidates, a few hundred candidates identified among a few 100,000 quasars, which look periodic if you do a simple Fourier analysis. And most likely, none of those are actually binaries or even periodic, because quasars flicker and they can mimic periodicities. So what's happening now, I think, is that the problem is that we don't have enough cycles. So all the candidates, all these few hundred candidates, which are periodic quasars which look like they have periodic fluctuations, those periods are of order a year. And therefore, we only have a few cycles, and that can be mimicked by stochastic noise from the quasars. That's why we don't have reliable measurements of quasars being periodic for sure. For shorter period variability, we could have many cycles, but those will be very rare, because from periods that are shorter, the in-spiral time is so short that we cannot find them among a few 100,000 quasars. So I just want to say that this, I'm very excited. This will change within the next 2 years because of the LSST survey. There will be, instead of hundreds of thousands of quasar light curves, there will be tens of millions of quasar light curves monitored every few days. And so we will be able to look for much shorter periods, which will be much rarer, but will be impossible for noise to mimic. So I'm looking forward to that, and we'll be sure that they're periodic sources. And then I don't have time to discuss more, but I think we can also convince ourselves based on if you see lensing-like signatures or Doppler effects in multiple bands, that they are actually binaries and not some other sources of periodicity. So I think I need to stop here. And I will not read out my summary because we are a bit late, but thanks.